Hi, welcome to Lab 3, where we're taking a closer look at black holes. So the objective is to find the mass of this black hole with the planet orbiting around it. To do this, we'll first review relevant formulas, then we'll use my email address as the seed to take a look at CoreScript to find the star's trajectory. Then we'll review and analyze the animation, find the mass of the black hole with the net force, star's position, and the star's mass, and then we'll close with some discussion. The key concepts are, first and foremost, Newton's second law. We know that the net force is equal to mass times acceleration. We also know that the momentum is equal to mass times velocity. With this, we could find that the change in momentum is equal to the net force times the change in time. Please note the net force is equal to the parallel and perpendicular components added together. The parallel component determines the magnitude, while the perpendicular determines direction. The gravitational force is determined by the negative gravitational constant times the masses multiplied over the magnitude of the radius squared. All times are had. So this is some of my glow scripts. You can see my email right there for the seed. The gravitational constant and mass of the star were given. This is the amount of minutes per day. And this is the formulas on the last side reiterated in a coding-friendly way. For instance, the initial momentum is equal to the mass times initial velocity. Final was the same except the final velocity. The change in these values are final minus initial. The net force is equal to the change in momentum. This is because the only force acting in the system is the force of gravity. So all of the changes added together equals the net force is just the change in momentum. This is the directional force for momentum. And some more glow script. So we can see right here that the parallel component of the net force is equal to the parallel component of the change in momentum. Same for the perpendicular force. This is probably one of the most important lines. The mass of the black hole is equal to the magnitude of the net force times the magnitude of the radius, which is the distance between the star's position and the origin. Also known as the planet, squared divided by the mass of the star times the gravitational constant. This determines where the arrows are on the animation you'll see in a moment, and I just asked it to print all of these values for us. So here's the glow script animation. You see the black hole in the middle and the planet orbiting around. You see that the magenta arrow is the parallel component, so this is tangent to the orbit. The blue component is the perpendicular force, and it's towards the center or black hole. The orange component is the net direction of the net force. The force of gravity is also stronger when the planet is closer to the black hole. You see this by the growth and retraction of the arrows. Please note there could be a possible error in this graphic because we assume that the force of gravity is the only force acting on the system. This is oftentimes not the case in real life. So with this, these are the printed values. You could see all the different weights we found, and through the average and through this formula mentioned earlier, we find this to be the mass. These are the other results that we asked the data to print for us. So discussion. How does the net force differ from the rate of change of momentum? These values are numerically equivalent but differing conceptually, so we know that the net force is equal to the parallel plus perpendicular component, and we find this to be equivalent for the change in momentum, and therefore these values are equal when the force of gravity is the sole force acting on the system. So we see these differ conceptually because F net leads to a change in acceleration, which leads to a change in velocity, which leads to a change in momentum. So it's essentially a cause and effect issue where F net leads to change in momentum. A change in the net force leads to a change in momentum. We can also see the net force is the sum of all forces on the system, while the change in momentum explains the changes in speed and direction solely. Next, what happens if the black hole is swapped for another black hole and the star's motion did not change? It would be impossible to find a new value for the mass of the black hole in this instance because we calculated the mass based on the net force, mass of the star, and distance between the masses, and these would all remain constant. Therefore, this new mass would have to be equivalent to the original mass. Thank you for your time, and I hope you have a great one.